Better.
Slightly better, okay. Maybe we'll have that light off and this light on. We might have to change. Yeah, okay. It's a bit more light on this page without the glue. So, well, we'll just do a go through here, and I'll not have much of a pointer, but okay, so we'll use it. So, we've got the electrocardiogram here. So, it's a little small, perhaps for people right at the back there, but this way we get everything on at once, including the little explanations at the bottom. So, a P wave electrically signals what in the heart? The atria are going to depolarize, which means that the resting potential of negative 90 millivolts inside is going to get less and go down to be 0 or even slightly positive inside due to the influx of sodium. So that's at the cellular level, but altogether, in terms of the heart, we're seeing a little blip of electrical activity, and once the atria depolarize, something has to happen to them.
Contraction.
They have to contract, right. They depolarize, successfully reach threshold, which they're going to because of the leaky channels of sodium, then it's going to contract. And that's what we're seeing here. This is talking about the amount of pressure in each chamber. So the little red line here, the atria, give a little bump of pressure. And because the AV valves are open, the ventricles are also going to feel that pressure. So they feel a little extra bump because they're kind of connected to the atria at that point. They're acting like one chamber. And a lot of the ventricles are fairly full already from just collecting blood, since they're larger than the atria, but then the atria squeeze and they give a little bit extra. They probably give a little bit more extra than that's trying to show. That looks like almost nothing extra, but it's just artistic license. That'd probably be a good 20 to 30% thing with all of the oracles and everything. So, but anyway, it gives a little extra bump. So the ventricles are now as full as they can be, and so it's going to be the so-called end diastolic volume. At the end of diastole, the ventricles are as full as they're going to be. Technically, I guess they wouldn't be literally as full as they're going to be until the AV valve closes, because another drop could still get in there. Until the valve closes, they're not actually as full as they're going to be. So, but at that point would be the end diastolic volume. So, but in the meantime, we had this sort of place where there wasn't much electrical activity, but there was plenty of physical activity in the heart, and we needed to get that contraction over with before the atria repolarized somewhere in here. But in terms of electrical activity, what we really see here, we don't really see the atria repolarized, because that would just be a tiny little blip. We see the QRS, which is the ventricles depolarizing. Then the ventricles are going to contract, and when they contract, now we're going to see pressure, a big pressure change, enough to start changing whether the valves are open or closed. So the first thing that's going to happen is the ventricle's pressure is going to get higher than the atria. So if there's more pressure this way than this way, or this way from this way, that's going to close that valve. It's just pushing harder that way. It doesn't take much, because the atria are under pretty low pressure, so the ventricles just have to start squeezing, and this AV valve closes, and we've now got all the blood we're going to get. We're now at end diastolic volume, and both valves are closed while pressure builds inside the ventricles, and that's what it means by an isovolumetric contraction. The volume of blood can't change in the ventricle because both valves are closed. Eventually something's got to give, but for right now it's contracting and squeezing the same volume of blood. Well, it's going to open the valve if it can, and it soon will. So when the valve closed, that's when we get the lub sound, or the first heartbeat sound, right here. Then the ventricles squeezing. No change in the end diastolic volume because nothing's opened up. when the ventricle pressure reaches the diastolic pressure in the aorta and overtakes it, then the semilunar valves open, and now we are going to have blood starting to go up. So as the pressure mounts here, and once the aortic valve is open, the left ventricle can start squeezing out its blood, and the amount it squeezes out is the stroke volume, and the amount that's left at the end of systole is the end systolic volume. So if we take the end diastolic volume and subtract out whatever got squeezed out, we're left with the end systolic volume. So this is the remainder. So now, during the period where the semilunar valves are open, it's almost like the ventricle and the aorta are acting as the same chamber in terms of pressure. So now, these two lines are moving in unison. Before it was these two. Here, because no valves were open, the ventricles just build the pressure. So it builds the pressure up here. Meanwhile, down here in the atrium, we had a little bump, which we didn't quite mention there. So that little bump comes from the fact that when the valve closes, it's pushing up. I mean, these valves are dangling like that, so all this blood that's right there, as the valve closes, is going to be pushed back in the atria, bulging it out a bit, and that's what causes that brief little bump right here. Doesn't really have a particular name, but it does over on this side, and we'll see how that's going to come about. So the contraction's over, and the ventricles are starting to relax. So now, instead of really tightening up, they're starting to loosen, and the volume is expanding a little bit. So the pressure starts to drop inside here, and only once all of that contraction, once the muscle twitch is over, only then are we going to get repolarization occurring of the T wave, just like this had to be over before it repolarized for the atrium. Now the ventricle is repolarized in the T wave, so we got to have both valves closed at the same time. You can never have them both open at the same time, so a valve's got to close first. Semilunar valves are going to close at the point when the ventricle pressure drops below the aortic pressure. As soon as that happens, and there's more pressure this way than this way, you can see there wasn't a lot of pressure difference. So pretty quickly, the pressure in here is lower than here because it's starting to expand. The blood starts to come back but can't get anywhere. So it would actually feed the coronary circulation at that time, but it's prevented from backflowing into the ventricle. Still can't open this valve because the pressure in here is still higher than in here. It's got to fall below, and so the ventricle's got a way to go. So this is the isovolumetric relaxation, so-called. In other words, the heart's relaxing, but it's the same volume of blood until the semilunar, still the AV valve, the bicuspid valve, as it would be on this side, or mitral valve, opens as soon as the pressure is lower in the ventricle. As soon as this pressure drops below here, well then, two people pushing on a door, this person's pushing less hard, the blood would start to flow in and fill up again. So now, we've got the ventricle starting to fill again. These two chambers are in unison because the AV valve is open together. Over here, I've got a little pressure bump, kind of like this, because when the blood did start to come back and push against there, it caused a bit of pressure against the aortic wall, which helped drive the blood into the coronary arteries. So that's the so-called dicrotic notch. And then after that, the aorta is giving its blood to the body, so pressure is decreasing, but blood is building up in the heart, so the pressure in those is rising as it fills. And now we're back to where we started, except to mention that the dup sound, the second heartbeat, occurred at the point where those valves, that semilunar valve closed, it made a second heart sound.
So I thought the lub sound was when the first AV valve, when the AV valve closes.
It is, yes.
Oh, okay, and then the dub sound is when the semilunar valve.
Correct. So the first heart sound is here. That's the, I think that's the lub sound, and the dup sound is this one here. Did I say it the wrong way around?
No,
Oh, okay.
I said it right. I think I screwed it
Okay.
up. Can you
I don't know why they give them such strange little names, but anyway, so that's it.
Can you say it again with a little bump in the pressure graph in the atrial systole? What's the second bump?
The second bump, you mean this one here?
Yeah.
It's the same sort of thing as this. It's happening because, see how the valve's kind of dangling down like that? All of the blood that's sort of in this area is going to get pushed back when that valve closes. So it's going to make the atria bulge a little bit because a lot of that blood's getting pushed up against it.
So it doesn't all go into the ventricle. There's some that gets pushed back.
Well, right. I mean, anything that's caught behind the valve, what I mean to say is when the valve is limp, it's kind of hanging down here, but then it's going to get pushed back like that.
Okay.
And so that causes an artificial bump in the atrium a second time. And the first one is due to the atrium contracting. The second one is due to the reaction to getting the valve pushed up against it. And this one, this little dichrotic notch and its resulting bump is the similar type of thing in the aorta. Only this time, instead of the valve getting pushed up against it, what's happening is blood's coming back, and it's stopped almost right away by the valve closing, but then it's causing the wall of the aorta, instead of being like this, they're going to briefly do that, and that's what that is doing. And that helps the current, on the left side, helps the coronary arteries get the blood. On the right side, there is no equivalent artery mechanism there, but it happens the same way. Yeah?
So could you say that the diathoracic notch is when the ventricle pressure